So hello once again. We're going to be working once again with real gases, but now we're going to be introducing other equations. And remember that the ideal gas equation is the one where PV over RT equals 1, where V is the molar volume. This is once again cubic meters per mole or volume per mole. And we have now what we call the virial equations, and the virial equations are going to add terms. Let's say we're going to be adding V over the molar volume plus C over the molar volume to the squared plus D over the molar volume to the cube, and so on and so forth. And V, C, and D are constants defined by equations. It is important here to talk about the eccentric factor, and this is a parameter which is introduced by Pitzer in 1955, and it's going to reflect the geometry and polarity of the molecules. So far, the ideal gas equation was stating that these are like very spheric balls, all the molecules, which, well, they do not attract, do not repel, they don't have any given interaction. And the eccentric factor, which is denoted by this letter omega, is going to be different for different substances. For instance, we have ammonia, we have argon, carbon dioxide, and we can look for a lot of them, okay? And in the virial equation, when we just have the first term, V over V, we can calculate V, this parameter, as this expression, R critical temperature over critical pressure, V0 plus omega V1, where V0 is this expression. It introduces the reduced temperature. Remember that the reduced temperature is the temperature over the critical temperature. And this expression of V1 also uses this reduced temperature. And the van der Waals equation is another equation that is also very important. Here, what you have are two parameters, which are B and A. And B and A are parameters that are accounting. A accounts for the attraction forces between molecules, and it only depends on the critical temperature and critical pressure. And B is going to account for the volume that is going to be occupied by the molecules. So to the total volume, you subtract this volume occupied by the molecules. There are other equations. For instance, we have Redlich-Kwong. Here you have an expression where you add a temperature to the power of 0.5, and still you have A and B parameters. They are kind of different, but still you are working with the critical pressure and critical temperature. And then afterwards, Soave was working with Redlich-Kwong, so he did another equation. He introduced a parameter which is alpha. In this equation, A and B are these expressions, but alpha is depending on the square root here of the reduced temperature. Once again, the temperature over the critical temperature, but it also introduced the eccentric factor omega, okay? And another very popular one is Peng-Robinson. Peng-Robinson is kind of, it's kind of larger, and the question here is A and B are also different, depending on critical temperature and critical pressure, and it also introduces the eccentric factor in this term, M, which is in alpha. Now, these equations, probably they seem very straightforward when you solve them for pressure, but if you solve them for volume, then they start to become complicated. And then, especially if you have this term here, that alpha depends on the reduced temperature, which is depending on the temperature, then also the temperature has its issues. So when solving these equations for volume, molar volume, or temperature, then it will get complicated. It is easy for pressure, but not that much for volume and temperature. So most likely you are going to be working with either proposing values and just searching for this molar volume or temperature, or with software. And in these equations, remember, If you have a mixture, you can always use case rule to get the pseudo-critical pressure and the pseudo-critical temperature of the mixture in order to plug them, let's say here for A and for B, if you need so, okay? Also, if you need the pseudo-reduced temperature, you can always use case rules for the mixture. So this is about everything we have to talk about real gases. Thank you very much.